Okay, so today we're going to get into graphing linear equations. Chapter 4, Section 2. Okay, so the solution of an equation that has two variables. Look at that. Here's an equation, x plus y equals 3. Two variables, x and y. Give me a solution. Can anybody give me a solution? Lauren.
1 and 2.
She just said 1 and 2. So her solution wasn't just a single number. Does that make sense?
Yeah.
So her solution is, are you saying that x is 1, Lauren? If x is 1, then y is 2. Is that a solution?
Yes.
So she's giving us two numbers, x and y. And two numbers represents what? An xy pair represents what?
A coordinate.
A point. The coordinates of a point, right. A point on the graph. So are there other points that could make this statement true? Like if we didn't use 1, 2, give me another solution. Nico.
4 plus -1.
Good. So if x was 4, y could be -1, right? So how many solutions are there to this statement? Ryan? Infinite, right? Okay, so infinite solutions. So one quick question that you're asked usually at the beginning of this type of topic is this point a solution of this statement? X plus 2y equals 5. So you're simply testing to see if the given point is a solution. So how does a person find out whether it is or isn't? How can you find out, Bianca?
You could test it.
And how do you test things? How do you test points?
You plug them in.
Good, plug it in, right? So she's going to take the x and put it in 4 plus, and put the y in, 2 times -½ and say, does this equal 5? So what is 2 times -½ Do you know?
It cancels out.
What?
Doesn't it cancel out?
It feels like it's canceling out, and so what do you get when you have 2 times -½
Yeah, -1.
You get -1. So this is saying 4 plus -1, does that equal 5? 4 plus -1?
No.
No. So we would say this is not a solution. And you can abbreviate, just say NS. It's not a solution. Where is it? Oh, it's frozen. But it's not here. So the graph of an equation in two variables, the graph of this type of equation. If we went back and graphed that equation, the very first one here that we were talking about, x plus y equals 3, it feels like what we did on Friday. What does that graph look like? No one told us which x values to use. So what does that graph look like? Anyone else? Anyone else? Emily? A line, right? So it goes on and on. I mean, a line by definition is infinite, right? So when we graph an equation in two variables, it represents all the possible solutions of that equation by connecting the points of the known solutions. We find a few known solutions, we connect them, and we extend that. So, and because, obviously we're starting with the most basic type of function, which is a linear equation. And a linear equation gives us a graph that looks like what we were just describing, right? You see the little word of this type of graph in the word linear. And it is not going to look like an ear. So the little word is a line. We're graphing lines when we're graphing linear equations. So when you hear that word linear, or someone says, here comes a linear equation or something, you think line. Okay? So we're really going to explore linear equations. And you know a lot about them from last year. The standard form for a linear equation is given by this. This is the model. AX plus BY equals C. B may not equal 0. It would wipe out your Y. We can talk about that as we move forward. So A, B, and C are constants, numbers, right? X and Y are the points that are solutions of this graph. So if we're given a specific equation, this is a specific equation, right? This up here is, who remembers the term when we aren't using a specific equation? It's a, begins with an L. We talked about it the last part of chapter 3. Say it, Faith? Literal. Everyone say it. Literal.
Literal.
This is a literal equation, which is kind of like a formula, right? Or a model of a linear equation. Here's a specific equation. 5x plus 2y equals 28. So which of these numbers here represents C up here? Everyone? C is
28.
28. There you go. And because we have the exact form that you see above, A is represented by what number? 5. And B is 2. So if we receive an equation that looks just like this model here, then it is in standard form. AX plus BY equals C. Okay? Our favorite form, though, is
Slope Y
intercept form, which, can you remember what it is? I just kind of showed you. Plus B. So we're going to get to that, and we're going to continue to use that tons, because that is a very useful form, isn't it? Mm-hmm. So when we use this form, just as a review, what does M represent, everyone? M is the slope. That's why it's called slope y-intercept, right? And B is the
intercept.
y-intercept. Okay, good. So here we have an equation. Is this equation in standard form? So could somebody put it in standard form?
Yes.
What would it be in standard form? Ryan? Well, standard form is simply AX plus BY equals C. So we simply need to put the X term in the first leading position, right? Which would be just 3x plus y equals negative 2, right? But if we're asked to graph this equation right now, what form would you rather have it in? Slope y-intercept form. Or we also call that, when we have the y value isolated, we call that what form? It begins with F. Everyone say it, function form.
Function
form. So let's go ahead and put this in function form. And so do that for us, Jonathan. How do we put it in function form? We want y isolated, so what will we do? From both sides of that fence, which is the equal sign, right? Make sure you're doing it from both sides of the equal sign. Okay, so y equals, and what would you say? Or you could say negative 3x minus 2 as well, right? And so we kind of like that form. It looks like slope y-intercept form, which we're going to get to. Okay, we still haven't gotten there, so let's make a table. Let's make a horizontal table today, since we made a vertical one the other day. Let's get 5 values. What is that value that we really love to input? 0, so we might put that kind of in the center. And as we talked about the other day, we might have a couple negatives, a couple positives. So what would be some easy numbers, Zach? Okay, good. So let's just plug it in, right? And when we plug in 0, we get?
negative 2.
Anyone else as fast as Nico here? Let's plug in 1 this time. Plugging in 1. Be careful, there's some negatives involved here. When you plug in 1, you get?
negative 5.
Good job. When we plug in 2, we get? Good job. Plugging in -1 is kind of fun because it wipes out that -3, right? The negative times the negative. So -1 gives us
1,
1, right? -2 gives us,
4,
let's see, we have a pattern in our domain, right? What's the pattern here as we're going
One.
to the right?
add 1,
+1, +1. What's the pattern as we're going to the right here?
-3,
-3, -3, -3. And so when we have a very organized pattern in the domain, we see that beautiful pattern in the range too, which is nice. And now we simply go plot. So we plot them. Who's done plotting them already? You've already drawn it. 0, -2, 1, -5. 2, -8. -1, 1, -2, 4. That's a line. And there you go. We draw the line. We were not given a specific, like 3x value, so we draw the line. We could find every possible solution if we kept doing the math, right? So you might already know what I'm talking about. We do have two special linear cases. Special cases. And here we go. Before we identify what they are, so leave a little spot underneath your header there, linear equation special cases. Let's go graph them. So the first kind is y = 3. So this is a really strange equation, and when people first come upon it, they feel a little mixed up because there's not what? There's no x visible. It's just really strange looking. And so, but when you are told that this is a linear equation, it'll say graph these linear equations, and it'll say y = 3. This is not just a number line, like a point. This is supposed to be a linear equation, and y = 3. So we can still choose the x values that we love to choose. Let's say we love 0, 1, and 2, -1, -2. But regardless of the x value, what does y equal?
3,
Y = 3. So filling in the table even feels a little hard at first, but you can see how easy it is, right? No matter the x value, y is 3. Now we go plot this on a graph. This graph has 10, a scale of units are each worth 1. And so if I go and I plot any two of these points, and sometimes it's really important that you go actually plot them carefully, because people get very mixed up on these special cases. So when we plot, let's plot this one here, 0, 3. Walk 0, fly 3. And then let's just go plot this one out here. Walk 2, fly 3. So we could even plot this one out here. Walk -2, fly 3. And what type of a line is forming here?
horizontal.
Do you see that? It's horizontal. No matter where the x is, this should be right on that line. No matter where it is, the y's are all 3. And so when we have an equation that says y = 3, what type of line is this?
Linear.
What type of line is this? Horizontal. Is that kind of strange? Why is y = 3 being a horizontal line a little strange? Emily?
Because it's like the y values and then it's like the
Right. When we talk about y values, don't you think a y-axis and you think up and down, y-axis, right? But when all the y's are 3, do you see that you keep flying to the same spot and you end up with a horizontal line? So it's there's a bit of irony there, that when the y = 3, we actually have a horizontal, not a vertical line. So what happens when x equals something? X = 2. Now this is interesting when we use a table, isn't it?
Yeah.
Because what may x be?
2.
X may be 2, 2, 2, 2. This is kind of weird. X is always 2. No matter what, X is 2. So the Y values actually could be different things. We could have 0, 1, 2, 3. We're not told what the Y values are. So when we graph this, we walk We walk to 2, x is 2, and x is 2 up here, X is 2 everywhere, so this is our line now. And what do we call this type of line?
Vertical line.
Everyone say it, vertical.
Vertical.
And look at the table. What is it, what's being, what are we told here? This is kind of weird. X is 2, y is 0. X is 2, y is 1. X is 2, y is 2. What is this table showing us here?
There's infinite solutions.
Yeah, but it's not a what?
Function.
It's not a function. Not a function. And yet, can we graph it? Look at that, we can graph it. We can graph something that's not a function. This is such a special case. And who remembers what the slope is of this? It's a free fall. No, 0. This is a 0 slope here. Flat. 0 slope, flat. What is it when you are free falling? The slope is not negative. It is, Lauren.
There is no slope.
What do you call it though? There is a name for that.
Infinite.
All rise, and what's the run? 0. So what do you have?
Oh,
Undefined. It's an undefined slope. So it's graphable. And here's a not a function that's graphable. And it's such a huge special case because of that undefined slope. So horizontal lines take on the value, or the model for them is y equals some constant, b. Vertical lines also have that same model, but now x equals some constant. Okay? Okay, have fun. You have plenty of time to work on this.